and that's stable, see? Whereas a first degree alkyl halide or a first degree alcohol forms a primary carbocation. This is not stable. So you know for SN1, this is the reactivity. Third degree is fastest, second degree a little bit slower, first degree even slower still. Now remember the mechanism for E1? Remember the first step, the slow step, the hard step in the E1 mechanism is formation of a carbocation. Right? Let me find it. The very, very, very first step, if the mechanism is E1, this guy leaves. You get the carbocation. That's a hard, slow step. Once this forms, it goes like a shot to the product. So if the E1 mechanism is operating, the first step, the slow step, is formation of carbocation. And just the same argument as before, a first degree carbocation is not as stable as a third degree carbocation. So remember this. For SN1 and E1, this is the reactivity order. So I remember that. Both for the same reasons, carbocation stability. All right, so you're going to see this on the next test. I'll draw a bunch of alcohols, a bunch of alkyl halides. I'll have a first degree, a second degree, a third degree. I'll say which reacts fastest or slowest by the E1 mechanism. So remember, third degree alcohols or alkyl halides fastest, first degree are the slowest. For the same reason as SN1. Now also remember this. What about the SN2 mechanism? Remember, it's exactly the reverse. That first degree, and actually we put methyl here to talk about substitution. This is not a first degree. This is called a methyl halide or a methyl alcohol. Does anybody remember the reason why these react faster and these react slowest? What was the argument that was used? Why is this a reactivity? Why does, for instance, why would this undergo a substitution reaction? Yep. By the SN2 mechanism fast, and this slow. This is the third degree, this is the first degree. The SN2 mechanism operating is exactly right. Stir it, because the nucleophile, let's make it nice and big. The nucleophile has to get in this carbon, and if you got too many other groups around this carbon, you can't get in there. So you're exactly right. Stirring argument is used to explain this phenomenon. Okay? All right, so that's the reactivity. We've already covered this test we just took, this one and this one. What about the E2 mechanism? You might say, oh, it's lumped down here. Well, surprise. E2 mechanism goes the same as the E1 and SN1. The third degree reacts the fastest, followed by second, followed by first. Now, we can't leave well enough alone. We have to explain this, right? Because I know you just died to know why is that. You don't want to go home tonight wondering why is that. So here is our hand-waving explanation. You don't have the stir problems with the E2 mechanism like you have with the SN2. Because remember, the SN2 mechanism, which we draw it a little bit. In the SN2 mechanism, you have crowding around the carbon in the center. Excuse me. If the SN2 mechanism is operating, you get your leaving group, you get your nucleophile, and then you got your other groups here. And so this is starting to come in, and this is starting to break. So you got some crowding issues here. See? If you have substitution by the SN2 mechanism. See? So these groups are big and bulky, you're in problem. That's why if they're hydrogens, it goes much faster. All right, what about the E2 mechanism? What's going on? Well, you don't have the crowding problems. You have a carbon, you have a leaving group, halogen or OH, you get your hydrogen, and then you have your base. And we put a big base here, what the heck? But this base can stay on the fringe. It doesn't have to get into the interior of the molecule and attack this carbon. It stays in the fringe and attacks this and this complete in the E2 vector. So crowding about this carbon here is not going to make any difference. Okay? Because it just stays in the fringe. It doesn't have to get in the carbon's face, so to speak. Okay, so if steric problems is not an issue, which is not, why does it follow this trend then? Well, what does the transition state look like? This is the starting material. Okay? And let me draw that same thing on the sheet here. Let's look at the starting material and the product. Remember, nobody ever knows what the transition state really looks like because you can't isolate it. But if you start with this, and you end up with this, start with. The base blows off the hydrogen, that gives you BH, and the electron flips down this phase, so that's what you know. So what does a transition state look like? Well, who knows? But it looks like you're starting to form, you have a single bond here, you have a double bond, so you're starting to form a double bond. Okay? And this bond is starting to break. And this bond is starting to form. And this bond is starting to break. And this stays alone, this stays alone. In other words, let's put this in a box. This is the transition state. The transition state has some double bond character. Let's put in some, actually I didn't need to put in these hydrogens. These are hydrogens for our argument. Okay, so there's some double bond character in the transition state. Now, is this a first, second, or third degree reactions? Substrate. Is this carbon that has a leaving group is attached to 1, 2, or 3 other carbons? And that tells you what it is. Okay, it's attached to one of the carbons. This is the first degree. Okay, and this is the slowest. Okay. Now, this remember the transition has some partial double bond character. Now, let's take and modify this just a little bit. Let's change these two hydrogens to R groups. Okay? And we have our transition state. Products would be, again, this. By the way, these products would be H, 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 and H. This would be R, R, H, H. Okay, we see. Now let's look at the transition state. Well, the transition state will have some double bond character. I'll have R group here. Stretching, this bond is stretching, this bond is forming. Which of these two products is going to be more stable? Top one or bottom? Bottom, because it's got more R groups. So this is more stable than that. This has 2 hydrogens, 2 R groups. That has 4 hydrogens, no R groups. So we know the more R groups around the carbon that's double bonded, the more stable it is. And then ask yourself, this has double bond character. This transition state looks a little bit like this. It has partial double bond character. Anything that stabilizes a double bond will stabilize a developing double bond. See? So this double bond is more stable. This developing double bond is more stable than this developing double bond because I have more R groups attached to this carbon. Here I don't have any. See, in other words, words, a third degree substrate gives you a more stable product than a first degree substrate. Therefore, this activation energy must be lower. This is more stable than this, has a lower activation energy, so the reaction goes faster for third degree alkyl because the developing carbocation is more stable. The developing alkene in the transition state is more stable here than the developing alkene in the transition state here. So that's the argument used to explain the fact. I'm not having to draw these pictures. Everyone knows I don't want to grade your work. Your artwork, I should say. Your work, yes, not your artwork. It probably be better than mine. But anyway, these are the trends and for speeds. If you want something to go fast, by the SN1, E1, or E2, third degree substrates react the fastest, primary react the slowest by this mechanism. If you have the SN2 mechanism operating, it's the reverse. First degree is faster than second, second is faster than third degree. So chemists can explain anything. Organic chemists, after the fact, they get the results, they get the information, they say, oh, obviously, here's what's happening. Okay, now I'm not going to ask you for the explanation. What I'm going to do is, this is the test we just took. I'm going to ask you a question like this, except it won't be, this one won't be here. This cannot undergo elimination. We're going to have two carbons to get a carbon-carbon double bond. So this is out. Now if I give you this, this, and this, and if I say which of these reacts the fastest by the E2 mechanism, you would pick first, second, or third. And if I said which reacts fastest by the E1 mechanism, third. Same one, third. So don't be fooled. Unlike the SN1 and SN2, this reacts fastest by the SN2. This reacts fastest by the SN1 because the trends are different. E1 and E2 are governed by the same speeds. The third degree substrates react fastest, both by the E1 and E2. Okay. Again, it's kind of a lengthy, crazy explanation, but it works. I think they show you. Activation energies. Sometimes it's good to see the picture. Page 350. See, so they just kind of show you that the transition state has partial double bond character. So the more R groups you have on these carbons, the more stable it's going to be. And so here's a kid. These are hydrogens. Let's say it's not as stable. If you have R groups here, it's going to be more stable. So that's because the transition state has partial double bond character. So they show you, E2 mechanism with the first degree substrate, highest activation energy. Second degree, the transition state is more stable. The product is also more stable. And the third degree, the alkene is more stable, and so is the transition state. So as you go from first degree, second to third degree for the E2 mechanism, the activation energy drops, so the reaction goes faster and faster. Okay, that pretty much takes care of chapter 8. Our next test is 8 and 9, is that right? Is that what it says?
8, 9.
I think it would be 8, 9. Let's see, you want to have a test next week? Let's see. Probably in, I don't know if it's 3 weeks. What's 3 weeks from today? It's not going to be.
That's going to be
So we'll start the chapter next week, the next chapter. We might finish it. If we don't finish it the week after, and then the week after I'll have a test. So 3 weeks from tonight, we should have our next test, just to make sure we keep it on. And the next chapter is, we're going to dump a bunch of reactions on. Not a whole lot of new mechanisms, just a bunch of reactions.